Okay, so we've looked at how to handle these derivatives with respect to velocity, and now let's actually apply what we've developed here in computing the necessary derivatives for the matrices of interest up here. So I'm going to scroll back up. Remember, these are linearized longitudinal and lateral equations, and we're going to now start working through these derivatives here, the forces and moments with respect to u, and with respect to v, and with respect to w. Okay, so we're going to work through those derivatives right now. And I'm just going to do a couple example ones. You'll see how this works, and then you can apply it to the rest, and I'll show you how they all work out. But let's start off with fx comma u. Let's look at the derivative of the force in the x direction with respect to u. All right. So the first thing I want to do is I want to come down here and recognize that any derivative of a function, or the partial of that function with respect to u, through small angle approximation, that we're going to say that that's about equivalent to the derivative of that function with respect to capital V. That's our free stream velocity. Okay, so I'm just going to write that down here to start off. So the partial of any function with respect to u is about equivalent to the partial of that function with respect to capital V. All right, so that's what we're going to apply here as we try to compute this derivative. So now if we come back up here, what we are looking for is the derivative of the x force in the body fixed coordinate system with respect to u. So we come down here to our aerodynamic forces and moments, and we say the x body force, this is the pseudo aerodynamic force. It includes the aerodynamics, so the pressure and viscous forces on the aircraft, plus the thrust. Okay, so this is our pseudo aerodynamic force. We want to take the derivative of this guy with respect to capital V. All right, and actually this Cx can be written as Cl sine alpha minus Cd cosine alpha. Well, we're going to evaluate the derivative at our equilibrium state. So remember, each of these derivatives up here that we're interested in, we're evaluating those at this equilibrium state where angle of attack is 0. So since the angle of attack does not depend on capital V, those are independent as we're taking the partial derivative here. So I'm just going to neglect this here for just a second. I'm just going to do derivatives with respect to Cx, and then we'll come back and apply Cx at the equilibrium condition. Okay, so let's take the derivative of this guy with respect to capital V. And so first I'm just going to, we'll just come down here and start writing this down. So the force in the x direction is equal to 1/2 rho v squared SW times Cx plus the thrust times, let's see, what was that? Thrust times cosine alpha t naught, right? Plus t cosine alpha t naught. Okay, so that's my force in the x direction. I want to take the partial of that, so x with respect to u, and we're saying that that's equal to the partial of that with respect to v, right, from this rule here. And so now if we just take the derivative of fxb, what we get is 2 times, so actually up here we have two things that can be functions of v, okay? That first term, so I'm going to use the chain rule here. So the derivative of the first is 2 times 1/2 rho v SW times Cx plus 1/2 rho v squared SW times the derivative of Cx with respect to v. Okay, so I just use chain rule there. And then plus the derivative of our thrust with respect to v times cosine alpha t naught. Now, since we're doing the partial derivative, we're holding everything else constant and taking derivatives only with respect to v, and so our alpha t naught does not change. The angle of attack of that thrust does not change with a change in capital V. Okay, so All right, so we can simplify some of this here. So we took the derivative, and now we want to evaluate this derivative at the equilibrium flight condition. But before we do that, let's just look at this guy right here. So this is the derivative of the x force, the aerodynamic x force, with respect to capital V. Now I can come back up here and look at what that c sub x is in terms of lift and drag. This is how we write the c sub x in terms of lift and drag. So what we're looking at here is what's the derivative, what's a change in our lift coefficient or our drag coefficient with respect to forward velocity. Well, it turns out that lift and drag coefficients are relatively independent of velocity for high Reynolds numbers. So let's see. So let's say at high Reynolds number, that higher Reynolds number lift and drag coefficients become independent of velocity. Now at lower Reynolds numbers, those can actually change, somewhat significantly. But most aircraft are flying at a relatively high Reynolds number, and then also at low Mach number. So this is so probably Mach less than about 0.3. Then we can neglect compressibility effects. Now, compressibility will also change our lift and drag as a function of velocity. So, if you increase your velocity and you increase your Mach number or your Reynolds number, at high Mach numbers, the lift and drag can become functions of Mach number. At low Reynolds number, they can become functions of Reynolds number. So we're going to assume, at least for the purposes of this course, we're going to assume that we're operating in this range here, that we're at a high Reynolds number, but a low Mach number, a Mach number less than about 0.3. And so we can actually neglect changes in these aerodynamic coefficients with respect to velocity, okay? So if you take a compressible flow class, then you'll learn more about how to correct these for Mach number, which there are a few different ways to do that, but we're just going to neglect it for the rest of this course, okay? Okay, so at this point, we can simplify or just evaluate the rest of this at our equilibrium flight condition. And this first term here, I'm going to write actually in this form here. I know that looks... So that 2 could have canceled out, but I'm going to leave it here. I'm going to pull it inside of a parentheses. So this is 2 times Cx evaluated at the equilibrium condition divided by V naught. Okay, so this is this first term here. So what I've done is our velocity here we evaluate at our equilibrium state. So we put a V naught. I'm going to leave this as V naught squared. So I'm going to multiply by V and divide by V. And that's simply to leave this as a dynamic pressure out here. And because we're going to eventually be non-dimensionalizing these derivatives, and so it'll be helpful to have this in this form out here. So I'm going to leave it like this out front, and then that's multiplied by 2, this 2 there, the Cx, and the V naught. And actually, instead of Cx, let's come up here and look at Cx evaluated at the equilibrium condition. So Cx at equilibrium is when the angle of attack is 0. And so sine alpha is going to be 0, so that disappears, and this is going to be a 1. So Cx is equal to minus CD. So I'm actually going to just replace the Cx here with we're going to put a minus out front and then put a CD right there. And then we've got this this term over here that we need to add, and I'm going to write that as T comma V, so that's the change in thrust with respect to velocity, times cosine alpha T naught, okay? So this is our dfxb du, so that was our first aerodynamic derivative that we needed to compute. And so this is how we would do it, and we can repeat this process. So for any derivative with respect to u, we can do the derivative with respect to v. And really what we'd be doing is walking through each of these. So what we'd need to do is the derivative of the force in the z direction with respect to u, which you can do, here's the force in the z direction. It has to do with CZ, which is going to be tied to the lift coefficient at the operating condition, or at the equilibrium condition, I should say. And then we're also going to need the derivative of the pitching moment with respect to u. Okay, so I've worked through one of those, and I'm just going to drop on the screen here what the other solutions would be. So here are all of the derivatives with respect to u. Now, I've included these other derivatives, derivative in the y direction with respect to u, moment about the x-axis, a moment about the z-axis. Those are 0 because of symmetry. And so anyway, so those don't show up in our equations, but if the aircraft is perfectly symmetric, which is something that we are assuming here for this analysis, then all you're left with are these other 3 derivatives. And we worked through this first one together here, okay? Okay, so let's now look at derivatives with respect to v. So, or little v, okay? So df dv. So that's our next derivative of interest. Let me come back up here and just show you where we're working. So these are the derivatives of our forces and moments with respect to little v. So what we do is come down here to our analysis here to figure out a derivative with respect to v is equivalent, or we're going to say it's roughly equivalent to a derivative with respect to beta times 1 over v naught, okay? So df dv is equal to 1 over v naught times df d beta, okay? So this is what we're going to apply now for derivatives with respect to v. So let's come up here and let's do this derivative as our example. Let's look at the derivative of the force in the y direction with respect to little v. So that's one of the things that we need. That's that guy right there. So let's work through that. So the force in the y direction is simply equal to 1/2 rho v squared SW times cy. Doesn't have any thrust because we're assuming that that's symmetric. And cy is just a cy, a coefficient of force in the y direction. So we don't need to lift and drag. We don't need to change that to be in terms of lift and drag. We just call that a side force, okay? So let's write that down. So our FYB is equal to 1/2 rho v squared SW times CY, okay? And what we're saying is that a derivative of that with respect to little v, which is the thing that we need, is equal to the partial of it with respect to beta times 1 over v naught. Okay, so so we can just take the derivative of this with respect to beta, and so that's going to give us 1/2 rho v squared SW times CY comma beta, and then multiplied by 1 over v naught, so 1 over v naught like that. And we'll just put this in parentheses, everything out front here. Once we evaluate this at the equilibrium state, then we put a little 0 there on the velocity. And there we go. That was a lot simpler, but that's actually the solution right there. So it's just the derivative, the change in that side force with respect to beta multiplied by 1 over v naught. Now again, these v naughts could cancel if we wanted, but I'm going to leave them. I'm going to write them this way just to simplify things later on. So let's look at all of the derivatives with respect to v. So we just worked through the force in the y direction, but here are the, let me put this on the next page. I'll shrink that down. And here are all of the derivatives with respect to little v. And the example that we worked through was this force in the y direction, and you can see that solution right there. That's what we came up with there. These other 3 are 0 because of symmetry, and but we'd also need this the change in moment about the x-axis with respect to v, so that's our rolling moment, and our yawing moment with respect to v. And so you can see what those turn out to be if you work through that, okay? Okay, so there's our derivatives with respect to v. And now let's just do one more example. Derivatives, so df dw is another one that we're going to need. So let's come back up here to our equations of motion. And for this one, let's go back to, so we're looking at derivatives with respect to w. And we'll just work through this first one, the derivative in the x direction with respect to w, forces in the x direction. So let's look at how we're going to evaluate that. So any derivative with respect to w can be written as a derivative with respect to alpha times 1 over v naught. Okay, so let's just write that down. So this is going to be equal to 1 over v naught times the partial of that with respect to alpha. So that's what we're going to apply. And what we'd like to do is look at the forces in the x direction. Okay, so we know what those are. So that, well, let's scroll all the way back up here. So force in the x direction is right here. So that's 1/2 rho v squared SW cx. And because I'm going to be taking derivatives with respect to alpha, I actually need to pay attention to these guys. These guys are functions of alpha. And so I'm just going to write this, and instead of cx, I'm going to put in CL sine alpha minus CD cosine alpha. Okay, so let's write that down. So the force in the x direction is equal to 1/2 rho v squared SW times CL cosine alpha minus CD sine alpha. Okay, let's just make sure we got that right. So we've got CL sine alpha minus CD cosine alpha. That's right. So let me just fix that real quick. So this is CL sine alpha times CD cosine alpha. Okay, and then we've got plus our thrust term. Come back up here to our thrust, and it's thrust times the cosine of alpha t naught. Okay, so we've got plus thrust times cosine of alpha t naught. Now that's the angle of the thrust. Okay, so now we're ready to take the derivative of this with respect to alpha, right? So actually what we want is the derivative of this, of fxb with respect to w, which we're saying is 1 over v naught times the derivative of fxb with respect to alpha. Okay, so we take the derivative with respect to alpha here, and what we would get is 1/2 rho v squared SW. So that's just a constant out front that doesn't depend on alpha. Now inside of this, actually the lift coefficient is a function of alpha. Sine alpha is a function of alpha, drag is a function of alpha, and cosine alpha is a function of alpha. So I'm going to need to use the chain rule on each of these terms. So what we're going to end up with here is CL comma alpha, the derivative of lift with respect to alpha, times sine alpha, plus CL times cosine alpha, that's the derivative of sine with respect to alpha, and then minus CD alpha times cosine alpha plus CD times sine alpha, right? Because the derivative of the cosine is negative sine. We had a negative out front, and so that's that. Now this guy, the derivative of this with respect to alpha drops out, so we assume that that's 0 because there's nothing in there that depends on alpha directly. Okay, so now we're ready to evaluate this at the equilibrium condition. So at equilibrium, alpha equals 0. And so several of these terms are going to drop out. So sine alpha there is going to drop out. Sine alpha there, this is going to go to 1. Cosine goes to 1. And so what we get here is that this is equal to 1/2 rho v squared SW. Oh, and we've evaluated this at the equilibrium conditions, so V is equal to V naught. And then this is multiplied by, we're going to have a CL minus CD comma alpha. Okay, everything else there dropped out. So that's our derivative of fxb with respect to W. Okay, so that's what we get right there. Now we can again work through this for the derivatives of the other forces and moments with respect to W, and let me just show you what we'll get there. So these are the solutions for each of those derivatives with respect to W, and again, several of them, or these three here, are 0 because of symmetry. And then, oh, I missed something here. This needed to be multiplied by 1 over V naught, right? So we've got a 1 over V naught here. And so that's where this guy comes from here. So we worked through this first example. We've got the 1/2 rho V naught squared SW out front. And then the 1 over V naught, I've neglected. That gets multiplied by it right there. And so, so this is what we end up with right there for the derivative, and you'll see that similar thing with these other derivatives. Okay, so we've now worked through our derivatives with respect to u, v, and w. These are our derivatives with respect to our velocities. And let's just scroll back up and make sure we understand why we did that and where we're going next. So what we did was we worked through these derivatives with respect to u, v, and w. And the challenge, or the reason we had to look at this, is because these derivatives are not written. These derivatives we came up with based off of a free body diagram using Newton's second law, and they weren't written in a form that was really useful to us in aerodynamics. In aerodynamics, we like to think of things in terms of alpha and beta, and also lift and drag. And so what we needed to do was estimate what these are in terms of alpha and beta and lift and drag. And so that's what we've done now. So we now have expressions for each of these. So we could, if we knew the aerodynamic properties of an aircraft, we can now estimate each of these derivatives using these equations down here that we've worked through. So things like this: 2 times the drag coefficient over our current velocity, lift coefficient, pitching moment coefficient, and then these derivatives with respect to beta. These are things that we would get out of aerodynamic software, out of a wind tunnel test, something like that. So these are in terms of aerodynamic properties that we would know about this aircraft. Okay, so now we can estimate each of these derivatives. We'll be plugging these now back into this equation eventually, back into these original equations. And before we do that, though, we have a few more derivatives to work through. And so the next ones that we're going to look at are derivatives with respect to rotation rates. So these are P and Q. Let's see, we've got derivatives with respect to Q right there, and then derivatives with respect to R.